Hello everyone. Here I have a problem statement for you guys. So let's read through the problem. The problem says that we have a 1-1 countercurrent heat exchanger designed to heat a single component process stream from 150 degrees Celsius to 180 degrees Celsius using the following type of heat exchanger. We have our hot utility superheated steam, which comes in at 50 Kelvin of superheated. The steam is at 10 bar gauge and at a saturation temperature of 184 degrees Celsius. The latent heat of vaporization is given and the heat capacity is given, both for steam and water. And we have the heat transfer coefficients: 1000 kilojoules per hour square meter Kelvin for the liquid system, 2000 for the superheated steam liquid system, and 8000 for the condensing steam liquid system. The process streams has a flow rate of 1000 kilomoles per hour and a heat capacity of 100 kilojoules per kilomole Kelvin. Okay. Now, our first question is going to be, what is the highest? Actually, what's the lowest? Let's start with the lowest possible outlet. The lowest possible outlet temperature of our steam utility. Now, this is more of a theoretical concept. Concept. We're looking at the upper theoretical limit of what's gonna happen. So let's say if you have an infinitely long heat exchanger. Here you have your process stream coming in, and you have your heating utility. Our steam is entering at 50 Kelvin superheat. Our saturation temperature was 184, so that means our inlet temperature was 184 plus 50, which turns out to be 234 Celsius. And our process stream was entering at 150, and it needs to be heated up to 180. So okay, let's see. If your heat exchanger was infinitely long, what's gonna happen is that both of these streams, your hot stream and your cold stream, their temperature, it's gonna mimic the action of mixing both of these streams together if you had an infinitely long heat exchanger, meaning this temperature, as the area of the heat exchanger tends to infinity, the outlet temperature of our heating utility is going to tend to 150 degrees Celsius, which is the inlet temperature of the cooling utility. So like I said, for an infinitely long heat exchanger, the temperatures are eventually gonna reach their thermodynamic limit. Once it hits 150 degrees Celsius, there's gonna be no more heat transfer, and that's the lower limit of how low this temperature can go. Okay, now I pose in front of you the question: what's the highest outlet temperature? Okay, in this case we were assuming that we have an infinitely long heat exchanger. Now in this scenario, let me bring forth another case. Same setup, but let's say this time the flow rate of our steam tends to infinity. Okay, and it's still entering at a temperature of 234 Celsius. Okay, so if the flow rate tends to infinity, that means that m dot times Cp tends to infinity. And if m dot times Cp tends to infinity, then delta T, whatever that is, and no matter how much heat you need, the amount of heat you need to transfer is fixed upon the requirement of your process stream, which in our case needs to be heated from 150 degrees Celsius to 180. So that's the heating requirement that we need. So that is fixed. And if you look at this equation as mCp as the denominator of this equation, of this fraction tends to infinity, delta T tends to 0. Hence the for an infinite steam flow rate, your T out is gonna tend to, it's gonna be equal to the inlet flow rate, and that's so that's the theoretical upper limit. Now deciding what should be the outlet temperature is actually an optimization problem, and once we start looking into optimization in more detail, we're actually going to cover that. Now I'm gonna find the area of this heat exchanger for an outlet condition. Let's say our T hot is coming out at, our steam exits the heat exchanger at 174 degrees Celsius, which is 10 Kelvin or 10 degrees of subcool in our case. Okay, now if I were to draw a temperature enthalpy diagram for this problem, I have my cold stream that needs to be heated from 150 to, hold on, let's see 150, 180. I have my cold stream that needs to be heated, temperature enthalpy, and I have my heating utility. Now the heating utility enters at 180, it enters at 234 Celsius. Okay, it becomes saturated at 184 degrees Celsius. And when the steam is condensing, the temperature is going to remain constant. And finally we set the exit temperature is going to be 174 degrees Celsius, so somewhere around here. So if you look at the countercurrent temperature profile, and if you were to use just the inlet temperature at one end and the inlet outlet temperature at the other end, if you took the log mean of those two temperatures, you would get, like, that would not work in this case, because you essentially have three sections of your heat exchanger. Taking the log mean of two temperatures only works if you have like a smooth profile between both streams, which in this case is not the case. Therefore, instead of just giving up, what we can do is we can divide this heat exchanger into three sections. So we're gonna have I'm gonna call this section 1. So the subcooled region. I'm gonna have section 2, the saturated region, and I'm gonna have section 3, the superheated region. Now there's a problem. We know all of the intermediate temperatures for our heating utility. We know it enters at 234, it becomes saturated at 184, and it exits at 174. But we don't know the intermediate temperatures of our process stream. Like, what is the temperature here? what is the temperature here. So in order to do that, we'll have to make use of our old friend, the energy balance. Okay, so section 1, section 2, and section 3. So our process stream is entering at, I'm going to call this TC1, enters at 150 degrees Celsius. TC2 is unknown. T3, and finally T4. And I know the temperatures of steam. Steam enters at 234 Celsius, becomes saturated at, I'm gonna call this, let's put 184 degrees Celsius, condenses at the same temperature, and finally exits at 174 degrees Celsius. So we have our flow rates. The molar flow rate of the process stream was given to be 100 kilomoles per hour, 1000 kilomoles per hour. The heat capacity of our process stream, I'm denoting C to represent the fact that our process stream is the cold stream that needs to be heated up. We have our heat capacity, and okay, the flow rate of steam. What flow rate of steam do we have here? Okay, oh yeah, okay, so we also need to find the flow rate of steam, which is not given here, and that's gonna depend upon the overall energy balance on this entire heat exchanger. So the heating requirement, your Q dot, is gonna be the molar flow rate times the heat capacity, T out minus T in, which in our case is the flow rate of our process stream, 1000 kilomoles per hour times 100 kilojoules per kilomole Kelvin, goes from 150 to 180. So our heating requirement is 3 million kilojoules per hour. So using this heating duty, we can find the flow rate of steam required. Now the steam needs to be condensed. The steam is entering superheated, so we're going to be using the heat capacity for the vapor phase, and there's energy associated in bringing it from 234 to 184, and then there is energy associated with condensing the steam, the latent heat of vaporization, and then there is energy associated with making it subcooled from 184 to 174. So we know Q, which we just calculated right here. The CPs have been given, the heat of fusion has been given, the heat capacity in the liquid phase is also given. Hence we can find the flow rate of steam, and that should be equal to 3 million kilojoules per hour divided by the heat capacity in the vapor phase, which is 2.1, yep, 2.1 joule per gram or kilojoule per gram. Times 234 minus 184 plus the latent heat of fusion, which was in our case 2000. Yep. And finally the energy needed to subcool the stream. All right. So once this has been plugged into my calculator, which I am gonna do right now, the flow rate comes out to be 1397.3 kilogram per hour. Okay. Flow rate found 139.7 kilogram per hour. All right. Now, in order to size our heat exchangers, we need to find these intermediate temperatures, because once we know these intermediate temperatures, we'll be able to use the log mean temperature difference. So for let's start off with our subcool section. Section 1 being our subcooled. Our process stream enters at 150. We don't know the temperature at which it's leaving. I think I called this T1, T2. Okay. And steam is entering at 184 degrees Celsius and leaves at 174 degrees Celsius. Okay, so first off, we can find the energy that steam gives off in this section of the heat exchanger, and that's just going to be the energy required to bring steam down bring saturated liquid water actually from 184 degrees Celsius to 174 degrees Celsius. So your Q dot is going to be MCP times TH in minus TH out, which is going to equal the molar flow rate of the process stream times its heat capacity, and heats it up from 150 to the outlet temperature. Okay, so once we solve this energy balance, the outlet temperature of our process stream from the subcool section is going to come out to, give me 1 second, this comes out to be 150.6 degrees Celsius. So not much of a difference. Okay, so once we have both of our temperatures, we can find the delta T log mean and use that to find the heat exchanger area. So the heat exchanger area is equal to Q UA delta T log mean. Now for every heat exchanger calculation, your two main equations are going to be the energy balance and the design equation. So in our case, our heat exchanger area is going to be the heating requirement divided by the heat transfer coefficient times the log mean temperature difference. And if you guys remember what log mean temperature difference is, it's just the temperature difference 1 minus temperature difference 2 divided by the logarithm of delta T1 divided by delta T2. And each delta T represents the difference between the temperature of one process stream and the temperature of the other stream. Alright, so we're in the subcool section. For our subcool section, our heat transfer area, our heat transfer coefficient was 1000. So A equals our heating duty, which was found to be 58686 kilojoule per hour, divided by 2000. Sorry. Times the log mean temperature difference, which turns out to be the temperature delta T1 is going to be 184 minus 150.6. $33.4 minus the temperature difference on the other side is going to be 174 minus 150. 24 divided by the natural log of 33.4 over 24. And if you work out your units, you're gonna find out that everything, like the units of this entire term, come out to be meter square. So plugging in the numbers in my calculator, okay, so the final area for the subcooled section comes out to be 2.06 meters squared. Now we're not done yet. This is just the area of the subcooled section. We still have to find the area of the saturated section and the superheated section. So we'll just continue this in the next video.